I didn't look yet. Did you post the new homework?
I did just now.
Oh, just now. Okay.
Right before class, yeah.
Was it what you said it would be about?
Yes.
Okay.
So we'll talk about it. Or is it actually time for class? All right, so that's right. So there's a new homework, which is written rather than typed up. So let me know if anything's unclear in terms of handwriting or in terms of physics. But the problem is basically sort of like I mentioned, which is let's try to suffer through a little bit how you would do psi-psi scattering with Wick's theorem rather than Feynman diagram. So at the very least, you basically have the back of the book, because you know the answer. The back of the book is Feynman diagram. You know the answer just in a second, writing down the rules, plus we did it in class. We started doing it in class the hard way, the Wick's theorem way, right? But now we want to, try to go through the steps to reproduce what you get with Feynman rules. This basically involves, the hard part of the calculation involves these manipulations with annihilation and creation operators, moving them around so that you can annihilate things on the vacuum. So, yeah, I don't think it'll be too bad. It may take a lot of scratch paper to get things so that you get a feel for what's going on. But you at least know the result that you want in the end, and we'll actually do a little bit of a similar manipulation today. So, this is basically the last lecture before we talk about quantum electrodynamics. The first, widely useful theory, I guess. I mean, Yukawa theory that we've been studying is a real theory at least, but sort of limited in its applicability to the real world. So let's also go back over I want to just state again the Feynman rules for our Yukawa theory, because I want to highlight two additional rules. So this is our Feynman rules for Yukawa theory. And in case Yukawa theory is too ambiguous, what I mean is this thing, I guess we call it lambda. So we'll actually, at the end of the class, we'll also look at a related interaction where, we were talking about all sorts of different fermion bilinears that you could make because we know about extra things like gamma mu could be sticking there, but then I need someone else to soak up some mu, 4 vector stuff. So if I only have a scalar, I still have another option besides 1 being in between, which is gamma 5. Right? That would be a pseudo-scalar interaction. Anyway, that's certainly allowed by all the symmetries, by Lorentz invariance and everything. So we'll take a look at that interaction by the end of the class. It's also related for people who are interested in dark matter. It's what gives rise to spin-dependent interactions in dark matter. But anyway, so this is our theory. Let me just state again all the Feynman rules, for just also so that they become more automatic for us, and as a review. So let's talk about incoming fermions. If I have an incoming fermion, so I draw a dot just to show towards the bulk of the diagram. So this is an incoming fermion, say with momentum p and spin r. So if he's a U spinner, right? We had a subscript for his spin, and momentum p. If he's an outgoing fermion, then he's a U bar. Anti-fermions are the opposite, and they also involve these instead of, and we draw the backwards direction for the arrow because we show the flow of a current. So he looks like a V bar R, and if instead, does this notation make sense with the dots? So the dot is towards most of the diagram, right? So the dots on the right, that means symphony, the dots on the left. Or, sorry, did I draw that wrong somewhere? No. I think that's right. The vertex, so that's fermions and antifermions. We know our one vertex. It's this, and that's a minus I lambda. And the other big thing we could do is propagate. Propagators, these are internal lines, right? And if you're a dashed line, that's a scalar, which we know is this I over b squared minus mu squared. I didn't say that our phi is mass mu and psi mass little m. And the only difference with a fermion propagator is there's a p slash plus m in the numerator. And he has a different mass because he has a different mass. So these are all the diagrammatic rules. Then we have some extra things like, you know, spinor slash matrix indices are contracted together. We'll see an example where actually later on that contraction of multiplying a bunch of matrices together with spinor indices is the same as just taking a trace of the multiplication of those matrices. We also have to insert, this is, so the last two rules when we write down are sort of a drawback of Feynman diagrams in a sense. I mean, you know, all of these rules are really fantastic and amazing and simplify everything. You don't have to worry about moving annihilation and creation operators around a million times with these rules like you do with Wick's theorem. But you do have to insert extra minus signs. Sometimes it seems hard to understand. Sometimes it's easier to connect it directly to Fermi-Dirac statistics. We'll look at a new example of this today. A new rule, basically, that will let you, that will, in a sense, add to this list of Feynman rules. That'll help us make sense of it. And another important one is, we'll also see, is another extra minus sign. Anytime you find for a fermion loop, we won't really encounter these in much detail in this class. This would be for like second semester class, focusing on renormalization and stuff. But we'll see why you have an extra minus sign today. We'll look at one loop diagram just for completeness. So that's also later today. Okay, so anyway, this is mostly a review of what the Feynman rules are for this Yukawa theory. And we'll spend a little bit of time today talking about these minus ones, basically, that will crop up when you're dealing with these anti-commuting spinners. There are anti-commuting annihilation creation operators. So there's certainly some subtlety to these minus signs. That's the very first example we're going to look at today. So last time, right, what did we do? We looked at psi-psi scattering, particle-particle, through the exchange of this new scalar. So now let's do particle-antiparticle, and then we'll look at a one-loop example of scattering. Then we'll go back to psi scattering and psi bar and look at their Yukawa potentials, do the non-relativistic limit, and then we'll also look at what happens when we stick in a gamma phi. All right, any questions about Feynman diagrams or anything before I raise? We haven't been super rigorous, right, in trying to derive the Feynman rule. I mean, we basically did derive the propagator, but these rules for internal lines and stuff, we didn't really derive really rigorously. We sort of just seemed plausible, basically. But now you'll get more, when you do this real homework calculation, you'll get a feel for how things go in the more formal way of calculating things with the Wick's theorem, and you'll see maybe how, some connection with the Feynman diagram. Okay, so let's do sidebar scattering. For the rest of our calculations, though, we're going to forget about Wick's theorem after this, actually. But let's first just do it the Feynman diagram way. And it turns out to really understand the minus sign in this case, you have to go back to Wick's theorem. But, okay, so what are our processes? So we're only going to do this at order lambda squared, so just two vertices that we can insert. So we'll have one that's very similar to before, but right now I have to have an antiparticle involved. So this is, psi scatters into a psi, and a psi bar scatters into a psi bar. And we want to take into account all the spin and momentum information. So this guy is P and S, this guy is Q naught, this is P prime S prime, and this is Q prime R prime. And there's another one now, right, a different type of diagram than what we had before, which is an S-channel diagram. So because we have a psi bar and a psi coming together, right, they can actually meet at one vertex now. Right, so this is very different than what we had for psi scattering. This wasn't allowed. I guess I'll keep the bring that downstairs. You always want to have the arrows following one direction through the vertex. So the labels are all the same. All right, so we can write down the amplitude straight away. But the ambiguity, which is sort of always an ambiguity with fermion calculations, is are we going to add the diagrams or are we going to subtract them? What's the relative sign here? So I'm going to tell you what it is, and then we'll dig into the Wick's theorem calculation and see why that comes out. But there's a pseudo rule that will allow you to do this from now on without having to go back to Wick's theorem. So both the diagrams have 2 minus I lambdas, right? And it turns out what we should actually do is subtract the 2 diagrams. So we'll put the minus sign in front of the first one. And what's our rule for spinners? Right, we're going to contract them at the same vertex. So this U bar S prime guy contracts with the U SP at that vertex. And the other ones, the other V and V bars will contract on the other vertex. We use V's, and we have antiparticles, right? And use when we have particles. So all that makes sense. And the only thing is now, what's the momentum flowing through that? It's P minus P prime, right? Prime. And the guy flowing through there has a mass mu. So that's for the first diagram. The second one, now a U and a V are actually meeting at one vertex, right? So instead of a U dot U bar, I'll have a U bar and a V bar contracting. U bar S going through here is just p plus 2. Right? And now close square bracket. And again, the big difference, physically, S channel has the possibility of this state not just being a virtual particle anymore, but being a real on-shell particle, which can lead to a big enhancement in the cross-section when the denominator becomes small. Right? So that's the resonance phenomenon. Sometimes those states are called resonances. They're allowed to be in the S channel. So it's pretty similar to what we had before. Remember, what we had before was the same diagram for psi-psi scattering, but we also had the possible interchange in the final states. We can't do that now because they're really different. They're not identical particles. A particle and an antiparticle. And just like before too, the two diagrams had different momenta in the propagators. But now it's a different combination of spinners, and now we have V's instead of U's, so it's certainly different. But very subtle minus signs. So I'll tell you a rule that will let us remember. For the minus signs. So before, basically, right before when we did psi-psi scattering, we had the T channel and the U channel. Those also had a relative minus sign difference because we could exchange two of the final state fermions. Right? Those were identical particles. So now our new rule for minus signs will be basically, so there's a relative minus sign difference or interchange to, say, incoming or outgoing size, say. So in the first example, that's why we had the relative minus sign difference. Or, this is the strange part in a sense, interchange an incoming psi and outgoing psi bar. So, these diagrams look very different compared to the similarity we had before with psi-psi scattering, right? But it turns out that we can actually just interchange, say interchange this incoming psi bar with one of the outgoing psi's to get exactly, we'll start with this diagram. We'll go the other way around. But yeah, let me just redraw this and I'll see that it makes sense diagrammatically as a rule for us to follow. And then we'll see also why we get that relative minus sign. So the rule, if I just apply this, so right, this is my really doesn't matter. Make sure I don't screw anything up. So what we're going to interchange are these lines. All right, so I'm going to, delete this incoming antifermion and replace him with this line. So that would make the diagram look like, right? Because I'm just, sorry. I'm just pulling this leg over, getting rid of that one, and doing the same thing. So now I delete this and pull that guy over. Does this manipulation at least make sense, what we're doing diagrammatically? So this is drawn in a weird way, but this is exactly this. Exactly the other diagram. whenever that happens, there's a relative minus sign difference. So you can remember that rule, or you can, go through the Wix calculation every time, make sure that you get relative minus sign difference. But this is infinitely easier than worrying about moving annihilation and creation operators around. And also, by the way, so I'm emphasizing a little bit the minus sign difference, which usually you don't care so much about minus signs, right? But I mean, it's super important, right? So for example, one important consequence of the minus signs are that it's going to control whether or not you have destructive or destructive or constructive interference, right? Because if you, I think that's clear. Let's write it out. Whether or not interference is constructive. Or destructive. Right? Since if we had two diagrams, well, I guess I'll write them in A. A1 and A2, or plus minus. Since this is what we're talking about. We're just talking about the relative sign difference between the two diagrams, right? We're either going to add them or we're going to subtract them. And we know that the physically relevant thing is the square amplitude, right? All the cross sections or decay rates will all be controlled by these things, square modulus. We'll have M1 and 2 star, M2 star, M1, things like that. But the sign, right, controls how we're adding the diagram. So that ambiguity certainly has physical relevance. Right? It's going to tell you whether or not the two processes add constructively or can interfere in a destructive way. So it certainly matters. And most of the time it is a pain to worry about fermions. There's no way of getting around thinking in detail about fermion statistics when you have these anti-commuting things. All right, so let's try to do it also the Wix theorem way, in a schematic way. I'm not going to follow around all the exponentials and everything, but like you will do for your homework. But okay, are there any questions about at least how to apply the rule? So, why? Where does this rule come from? Well, like all the Feynman rules ultimately comes from Wix theorem. So let's see how to do that. All right, so our initial states are basically, so I'm not going to worry about these factors of square root of energy and all that, but so I have to create a state incoming with momentum p, a particle, and I have to also create an antiparticle with momentum q and spin r, and I pull them out of the vacuum to create them, right? And there's a similar thing for the final state. It's all the same, but now let's try it. And remember, too, so I think I wrote this for your homework, right? what I actually will need is not the ket of the final state, but the bra. So that means I can think of them as acting to the left on the vacuum, and with the interchange order also. And also not without their diagrams. So this is again, right, redoing psi bar, psi bar, psi bar going to psi bar. So this diagram, let's focus on that. This is P going to P prime, Q going to P prime. What this is, what it matches onto in Wickster is some inner product from the S matrix. And we know how to calculate S matrix elements with the Dyson formula, which tells us some time ordering of Hamiltonian stuff. We don't like that. We want to write it in terms of normal ordered things. So what this will be is normal ordering on the fermions at two different space-time points. I have two insertions of the Hamiltonian. This is that second order. So that's why I have two psi bars, right? And let me now insert what the initial state is. So it's a BPS dagger, a CQR dagger on 0. All right? So this is also, oh yeah, there's also, I'm forgetting about the scalars because this is the minus sign comes from the fermion, so scalar stuff is just along to the right. But yeah, where are the scalars, by the way? What are the scalars doing in this sort of contraction, this application of Wick's theorem?
There's a, get that.
So there's a clue here, right? They're just propagating. So there's secretly here a Feynman propagator connecting points 1 and 2, which is the scalar propagator. Yeah. So that's all it is. I mean, the way we would usually draw that is with phi x1, phi x2, those things contracted.
That's
So
where
we never need to, basically we never need to worry about doing this funny contraction stuff. We just, because they'll always be replaced by propagators for us. But anyway, so those guys are along to the right, but we don't care about them. We're going to focus on the fermion stuff. And do this slowly too. So what we'll do is expand. So remember, psi looks like a B plus a C dagger, and psi bar looks like the opposite. So we're going to expand this. And first what we'll do actually is just expand these two. And we're only going to keep, so each of them have a B and a C, but we're only going to keep the undaggered version of each of these, because if we have any hope of the whole thing being non-zero, we need to create as many particles as we destroy so that the final initial states have overlap. Otherwise they'd be orthogonal. And you'd find that the amplitude's 0 or something, right? We don't care about the 0 contributions to the amplitude. So now our same diagram. So now we'll just do that first expansion. His expansion now will involve a momentum of K1, so that's easy to remember. The spin has some label, I call it M. It's somewhat redundant keeping track of the spin to end the momentum, because you can most of the time get away with only writing one label for each of your spinners. But here I'll keep it just be more clear. And right, we'll have also the annihilation operators associated with those, that field expansion. A2N and BP S dagger CQR. So is that all right? So only the B and the C survive, not the B dagger, C dagger. Yeah, for I and F to have overlap. To have non-zero overlap. All right, so let's just focus on that chunk of annihilation and creation operator.
Why did you choose to expand just the psi x2 and the psi bar of?
Basically, so that we'll be able to start putting it in some form like something that looks familiar.
Okay.
I mean, with spinners contracted in the right way, we know how things are going to work out. I mean, yeah, you can do it all at once,
Yeah.
but it just gets murkier.
Yeah.
So you do have freedom to do the expansion at whatever order.
Yeah.
Yeah. But I think it's, certainly easier than thinking about so many annihilation and creation operators all at once. So we have 4, so that's enough, I think. And our strategy is going to be to move, we want to move these guys, the daggers, leftward. Because any time a C or a B without a dagger is hitting a vacuum, that's 0, right? So this would be the same thing that happened before. Remember, a similar thing happened when we did a sketchy calculation of the psi-psi scattering. So what happens is that when the B and the B dagger change order, I'll also get a delta function, right? When they change order, now I don't have to worry about the state with the B being on the right-hand side, because B will annihilate the vacuum. That's 0, right? But I will get a delta function, which is physically important because it imposes relationships between the momenta and the spins, and it kills a lot of things. So, sorry, let me just rewrite this set of creation and annihilation operators. And we're going to use, I'll say it here, things like, BP, comma, PQ dagger, that's delta PQ. Right, so let me focus first on the B's in parentheses. So that means the C's that are surrounding him don't do anything, but now that becomes a delta function, which I'll write as a delta function on P, K2, and NS, and now the dagger comes first, and annihilation operator comes. There's a C there, C, Q, R dagger. So this part I can forget about. So technically too, right, you have to worry about, this will not be such a concern for you because in the psi-psi calculation for your homework, there's no C's, there's only B's. But don't forget too that they're not totally trivial. They anti-commute to 0, a B and a C. There's no delta function, but I would get a minus sign. But anyway, it doesn't matter because once I flip them, B hits the vacuum and that's 0. Minus 0 is the same, so it's 0. So this part I don't need to worry about. So I would get Now this is just ck1m with some delta function, ek, and bkn, sorry, b's are gone, and we have everything with just c's now. So is that step okay?
Sorry, why does it go to 0 again?
Oh, this?
Yeah.
So we can do it more slowly, but what I want to do, right, is just get, yeah, he's not right next to 0. If he was right next to 0, it would be 0, right?
Yeah.
But to get him to be right next to 0, I just change their order, and I get a minus sign.
Yeah.
That's fine, but it's times 0 anyway, so I don't need to worry about the minus sign, right?
Yeah.
So that's all I'm saying. It's still 0. Is
Okay.
that all right?
Yeah, just don't you get another delta out of it when you do that?
No, because of this. Because the b's and c's
Oh, yeah.
anti-commute
Right.
to 0, but a b and a b dagger anti-commute to a
Yeah.
delta function.
Right, okay.
Right. Sorry, everything else is just write b dagger is a delta, and the same for c dagger. These are our sort of quick rules. You know, all those guys have indices on them, but if you want to just follow the stuff that's not equal to 0, that makes it easier.
Yeah.
All right, so sorry, let me just again rewrite that. And delta is a delta, I'll pull the c's all together. P, K, N, S, 0. So this is really all that the homework will come down to. There'll be all their exponentials and things you have to follow. Actually, I probably need to give you one more hint about exponentials to do it. But then we'll do the same step now on the c's. Delta commutes with everyone, so it doesn't matter his order. He can go all the way to the left if it makes you happier. And the only thing I need to do is anti-commute these guys. And the same thing will happen, right? I'll have one term with a delta and one term without a delta. The term without the delta will annihilate on the vacuum. So this will become another delta function on the variables that I've flipped the order of. So this is super similar to what we had before. So that's nice too, because it means now these things that I invented, K1, which is some, dummy momenta for the momentum associated with my psi bar state. Now I'm told what my invented label is. It's just Q, which is some external momentum. So that's good. That simplifies things to being. I still have F. I have B bar are Q now, right? Now I know M is actually R, K1 is actually Q, so that's nice. So don't know what this state psi x1 is, I need to expand him now. That's the next step. And now also the UN K2 I know is S and P. So far so good. Certainly have to be awake when you're doing these manipulations. So now the only option that will survive, so we'll expand out these two states. The only part that will survive will be the sidebar x2. We'll have a UR spinner and some momentum associated with him. And I need him to be a daggered state so that he can hit the undaggered guy in the final state. Otherwise, I'll be pretty, and we'll say that that one is some L1 and right side is a C underneath L1 and so finally, or almost finally, our state. The final state I wrote, but all was 0 CQ prime R prime, CP prime S prime. So now I'm just expanding out the final state of these final fields, right? Inserting it there. So that then I'll just have a bunch of annihilation creation operators, some spinor contractions sandwiched between 0 and 0. So I have all that, these two guys associated with the final state, E3 prime, S prime, and now the CL1M dagger and the BL2M dagger, and spinor stuff. It's all weighted. BRR, Q, PM, L2, and the U's, U bar, N, L2, and U, S, P. So now the only relevant manipulation will be changing this order, right? So once I change their order, let me make sure I'm saying that right. Yeah, so let's do that. So don't forget, again, using that rule, B and a C anti-commute. Right, B and the C dagger also do. Anytime a B and a C are together, the only thing they can do is anti-commute to 0. There's no delta. So this goes to CQ guy, sticks around, nothing happens to him. I get a minus sign though now that I switched the order. Alright, it says minus C L1 M dagger and BP prime S prime EL2N S dagger. The same spinners. Just right the rewriting the whole thing. Hold that on 0. Yeah. So now I have it back in a form that I like. Right? Because all I need now to do the same sort of thing we were doing over here, where I want to get move things around so that I have the undaggered guys all to the left. Because the daggered guys all to the left and the undaggered to the right. Because the undaggered annihilate on the vacuum, so I only need to flip order once for that to happen. And I could do it again on this, right? So doing that, still have this relative minus sign, right? So I could do this as L1 dagger, C. Oh yeah, sorry. Let me. It is a lot of writing, but is it clear what I mean? Let me do one step first. And just leave the C's untouched for now. What happens when I flip them? I get a delta function, E prime L2 S prime N, minus the part that's 0, right? Times the same spinners. So I can do the same thing here. I'll get another delta function, but the minus sign remains. So this is the upshot of the whole exercise. That doing these things will really convince you one way or another if you have the sign. But for sure, it's subtle, because you make one mistake and you get exactly the wrong answer, right? It's the case where you really have to worry about minus signs. So in the end, this comes down to, right, doing this again, I'll have now, let me pull out the -1. This again will give me a delta function Q prime L1 R prime M delta P prime L2 prime. And this is all, u on u, which is 1, or sorry, 0 on 0, which is 1, times my same spinners. And you can check with these delta functions, if I insert those there, I get exactly the right spinner contraction that we have from Feynman diagrams. Right, so it's going to say, for this diagram, so L2 is actually P prime, so it's saying P prime and Q are connected on the, is that right? Yeah. Connected on the anti-spinner, the anti-particle spinner contraction. They'll get exactly the same answer that you have from Feynman diagrams, with the added bonus of getting the ambiguity of the minus signs straightened out. All right, so it's really just, again, using these rules many times, that you'll have B and D diagram anti-commute to a delta function, B and C's all anti-commute to 0. Which doesn't mean you commute them, it means you anti-commute them. So because something's equal to 0, you might think, I just forget about it, it doesn't matter the order, but their order does indeed matter. All right, so let's see one of the other Feynman rules that we'll add to our list. So this is to show you, for one, a little bit of how Feynman diagrams come about, right? Going through the spinner stuff and the work contraction theorem. But at the end of the day, you can remember how to get the minus sign from that rule of flipping lines. And we'll see how to get another one of the rules, which is if you have a fermion loop. So another example that we saw also when we did the scalar version. So let's again look at something which at first glance looks like it doesn't exist, but we know it does. What happens if we just have the scalars scattering on each other? So we can't do this at tree level. There's no process for phi-phi scattering, but we can do a loop that'll do it. Draw it as a box. So this is a process that would create phi-phi scattering. So we can have, again, our, say, P1, P2, P3, P4, or maybe we should use that notation, but. All right, and so there's basically one undetermined momenta in the loop that you have to integrate over. So we'll write down the answer using Feynman rules. So remember too, this is one of the new rules I stated before, which is a fermion loop equals a -1. So I'll insert a -1 out front. I'll argue at the end why that makes sense. So we have 4 vertices. So minus I lambda 4 times. And the undetermined momenta we'll call K. And we'll also use this rule about take care of matrix indices with a trace. This is another Feynman diagram rule. So we'll have 4 propagators to worry about, right? There's still just one undetermined momenta. So from the one undetermined K, we can figure out what the momentum flowing through any of the other 3 propagators would be. So the next will be K plus P1 prime plus k plus p1 prime squared minus m psi epsilon. There's a lot of propagators to worry about, a lot of slashes. The next one would be k plus p1 prime minus p1 plus m. K plus p1 prime minus p1 squared. And k minus p2 flat. That's a problem. So this is a bit different for sure than our other diagrams. It's our first loop diagram in this Yukawa theory. But it looks basically the same as the one we had before in the scalar theory. But now we have to worry about all of these gamma matrices, which are there inside of the slashes, right? The slash, again, it's just a shorthand for the 4-vector contracted with the gamma matrix. So there's a bunch of matrix multiplication going on, but which can be summarized as just taking a trace over those things. So some important differences though, by the way. So you could also notice that this is actually divergent, unlike the one we had before, which was accidentally convergent. So if I take k going to infinity, that's been our default integration, right? Which is actually totally wrong for us to assume. But we've been bold for, because right, if I take naively that limit, let me just count factors of k. Each propagator is a 1 over k, and I have 4 of them, right? So overall I have d4k over basically this, right? K to the 4th, because each one is a 1 over k. So d4k is like k cubed dk. But that's still not good, because that means I have a dk over k. Right? So this is really going, it becomes a log in the end, but it's still bad. It still will blow up if I allow myself to integrate over all possible momenta. So it seems weird, we'll need something called renormalization to deal with this. We'll try to have one or two maybe lectures on the very basic idea of it and how we can deal with those infinities. Renormalization, sorry. Let's also just try to understand the minus sign. And so note the extra minus sign. But this is actually general. So, this is one particular loop diagram that we wrote that happens anytime a fermion is in a loop, you get a -1 overall. This basically comes from the fact that psi bar is invariant. And inserted, basically comes from that. And psi bar is invariant. So let me be more specific. Before sort of the Wick version of this diagram, if I wanted to think about this in terms of contractions. So remember what we're doing, right? We're inserting the interaction Hamiltonian every time. Right? Interaction Hamiltonian is that vertex. Right? It is phi psi bar. And I need to do it 4 times. What I want to care about is every basically the contractions of the spinor fields in the loop. So let me call these points 1, 2, 3, 4. Every time I do that insertion, I get a psi bar, right? So for the first insertion, I have that. For the second insertion, I have same thing, and so on. But for these to become propagators, what propagators mean is go from 1 to 2, not 1 to 1, right? So to do what I should really, the way I should contract things is contract them in pairs, but on 2 different points, right? So in other words, the final and the first fields, those are the guys that have to be contracted with each other. So these 3 that are in the middle, they're fine. These are propagators, and they're invariants, right? It's a psi bar. So the only thing I need to do to put this in the same order, notice, right? Also, I always have the way of defining propagator is from psi to psi bar, not the opposite. So the only thing I need to do, psi bar, this psi 4, what I would like to be next to this psi 1, you can go through all of these guys. That's invariant, that's invariant, that's invariant. There's no minus signs. It's only when I change order in the last step that I get another minus sign. So you could show, that's the same thing, so I get a minus 1 now. I'm sorry, psi 4, psi 1, bar. And now everyone is happy. I have always field going to anti-field. And these are all just propagators, right? This is just, so I have minus 1, and now I have 1 to 4, or 4 to 1. 2. Right, and so I just have boring old propagators that I could have understood from just my Feynman diagram and calculation. But again, I get a minus sign because you'll always have this issue, the fermionic, right? You can also convince yourself the same thing happens with this diagram. I'll also have a minus 1. It's easier to show you because there's fewer fields involved. But anyway, so that's where that rule comes from. So totally general, always get a minus 1 for fermion loops. All right, so we may, yeah, we're mostly done now with Wick's theorem, at least for today. So, right, one of the important physical things we studied when we were doing the scalar version of Yukawa theory was the potential. I mean, that's a nice, simple to understand, low energy result, right? You can take the non-relativistic limit and match on with non-relativistic quantum mechanics and see what kind of a potential we get. And we saw before that it was universally attractive. So let's see if that's still the case when we have fermions. Potential now, fermions. So let's remember too, we did sort of last time. So before in the scalar Yukawa theory, right, our strategy, basically how we connected this with the ordinary non-relativistic potential, thing we usually call U in Shankar non-relativistic quantum mechanics. You could find out what that was by taking a non-relativistic limit of our amplitude, and matching into the Born result, basically. Born limit calculation in non-relativistic quantum mechanics. So we'll also need the non-relativistic limit of our spinors. So our spinors came with this weird square root of p dot sigma stuff. So we'll need to know what they look like at low energies. I guess we haven't talked about, but our amplitudes, right? And u and also v potentially. And we need to take the their non-relativistic limits. So what do we do? So what that means is we'll take our 4 vectors and replace them by mass for the 0th component and a 3 vector for the other 3 components. So this is not totally right? There's some correction to the energy. Right? But I could do some expansion, right? I use square root of p squared plus m squared to do the expansion, the lowest order thing, which is m. So remember what our spinner looked like? It was like p dot sigma times some spinner times a p dot sigma bar. Right, where these guys were just any 2-component spinner that satisfied this. So now we'll take that limit. So now I'll have p mu dotted into sigma mu, and now the biggest part of p mu is m. So this is just going to become square root of m times the identity, and then I just have the spinners left over. For this size, any 2 components. So that's good, at least, right? We recover our normal spinners that we know about in non-relativistic quantum mechanics too. And the only energy you care about in the lowest energy is the rest of that.
Is there a dagger in one of those spinners, or?
No, not in these.
Okay.
Yeah, so but if I want to do UU bar, which would be an invariant, then I would do that.
Okay.
Yeah. And spinners associated with the antiparticle has a minus sign. Sigma bar. So that goes to low energies from M and C minus. So this means nice things like the invariant, the U bar, say US, that will just be 2M and a delta function on those. Right, if I do UU bar, I'll get square root M squared, so overall M, and I can add the 2 because I'll have side add here twice. Right. And also, of course, we write down the other one. Things sort of invariant. Well, and by the way, also something you also could have guessed that without doing any work. Yes. What's the only possible thing everyone has to agree on that's an invariant at low energies, and it's the rest of it. The only thing you can have on the right-hand side would be that. All right, so we can go back to our size scattering. Remember, this is the way we think of potentials now, right? Even at low energy, quantum field theory is supposed to be this super general thing, works at high energies, low energies, and everything. So we can just calculate the scattering amplitude and take this non-relativistic limit to get the potential. So we can take our amplitude and make these replacements. We still have a minus I lambda squared. But now my spinner products I have in the numerator now become some 2n delta function. I have 2n overall. And spinners, which just come along for the ride. And S prime or delta r prime s for p minus q prime. They're now 3 vectors. So before I had 4 vectors squared minus the mass, and now 4 vectors squared is only minus a 3 vector. So now the 2 terms in the denominator just add. And we would do this matching, which would be the same actually, exactly the same thing we encountered. We did the scalar theory. Out of the Warren theorem says that is the integral of the plane wave over the potential u minus I prime. So basically the amplitude. Descend in some plane wave coming into the potential, scatter it. But the initial plane wave is p, and it scatters into some outgoing plane wave p prime. This should match on to this same amplitude. This should match on to, say, that first term. P minus p prime. Where else? Or actually q squared. So there is a non-trivial part. Everything in this case follows through basically the same as it did for the right. But by the way, you also get rid of this 2m because last time too we talked about the difference in different normalization we have. When we had relativistic normalization, there was a factor of mass that came in that didn't appear in the normal non-relativistic quantum mechanics. So to do the matching properly, we also have to normalize away that 2n. So this is the same exact expression we had before in scalar Yukawa theory. So we know the result. This tells us that the potential is a minus lambda squared. Remember how we would do this? You'd do some, do a Fourier transform, and then basically, there are different ways of calculating the integrals. We did it a nice way using a contour integral, but once you know what the momentum dependence is, if it's the same thing as we had before, the same momentum dependence, then it will have the same R dependence. So this is the same thing. The non-trivial part is that it's also telling us, because of these deltas, that spin is conserved in the interaction, which doesn't have to be the case. Spins don't change. The other thing is that we can redo this. This was for psi. We can repeat this for psi bar. Or also psi bar scattering. We didn't do that, but you could do it. And you'll find it's the same potential. Also attractive, has exactly the same form, no minus sign difference or anything. And this is ultimately because two minus signs come up relative to what we had in the psi-psi scattering case. One of these two minus signs cancel, which is kind of funny. One of these is from statistics, and the other is from the fact that instead of here we just had UU bar stuff, just gave us all plus signs when we take this low energy invariant. But in the case of psi bar scattering, you'll have some V bar stuff, which will give us a minus. So that's what we get two different minus signs from that give us the same result, whether it's psi scattering or psi bar. But one thing that certainly could be different, with scalars, we're not going to get any other momentum dependence or any other, be careful. You can get different momentum dependence, but we're not going to ever find something that's not attractive. So that's a totally general thing. Scalars are universally attractive. But one thing we could look at that would be very different is what happens if this is scattering through not just a scalar, but through a pseudo-scalar interaction. So that would mean we involve someone who can now change spin in the interaction, even at low energy. I know some people study dark matter, and this is the type of interaction that comes up there that's studied. But you could have also a variant of the Yukawa theory, where instead Lagrangian has a minus lambda phi, and now things sitting between psi and psi bar is a gamma 5. So this turns out actually to also have different momentum dependence, in addition to having spin dependence. So part of the upshot of having that detour into representation theory of the Lorentz group and all that was we got to figure out the world is bigger than just the identity matrix, right? There are a bunch of gamma matrices around, especially when you're using spinners. So there's no problem with writing down this interaction. It's totally Lorentz invariant. It doesn't violate anything. We can still even preserve parity. We specify that psi gets a minus sign under parity. So parity is still conserved globally if under parity this guy goes to minus himself. And we always get a minus sign on the space. But so if he does that, if he has flip sign under parity, he's called a pseudo-spin. So we can still do psi-psi scattering. But now with a new vertex. So instead of just minus I lambda, it would be minus I lambda gamma phi. So it's all the same, nothing changes except that rule. So we still have our same diagrams. This is P to P prime, S prime, Q R, Q prime R prime, and so on. So everything's the same, except we have these gamma 5s floating around. So same contraction. Say for the first diagram, I'll have a P and a P prime contracted together, right? But now it's sandwiched between a gamma 5. gamma 5 u r cubed, and with some denominator e minus p prime. Now let me just write actually the first diagram. I think we'll focus on one to illustrate what's unique about it. Okay, so at first glance, this is 0, actually, because gamma 5 looks like 1, 0, minus 1. So, looks like if I just do that multiplication with the non-relativistic limit I had before, where u just looks like c with the square root n in front, that's just going to be 0. So it's true that you get that if you just use that expression we had before, but don't forget, right, we only kept the first term in the non-relativistic expansion, right? We just kept the rest names. So if we go to next order, we have some momentum dependence. So this is true, this is 0 at lowest order. If we go to the next order in P, the 3 vector, then these spinners, so these guys of course have momenta in them. This will go to mass times CS prime transpose minus prime momentum, and daggered into the sigma matrix vector. So it's just taking that p dot sigma expression, taking the next term in the expansion, and you'll get that, which is importantly not 0, also has weird momentum dependence compared to what we had before. Before this was some constant, right? And also weird spin dependence. It's totally different. I'll write down what the final result is. This turns out to be the class of interactions, again, if you're the dark matter version, that's probably the hardest to see for if it's something WIMP-like. So with this diagram, this will become plus Im minus I lambda squared, and this weird spinner thing, prime transpose E minus P prime sigma CS, and another set of spinners, but basically where I flip S and S prime and S and R. So avoid writing that whole thing out. So right, compared to before, compared to this interaction, I just had no gamma 5s. Compared to just the regular scalar Yukawa theory, so it can change spin, or is what's called spin dependent. So this changes spin and has more suppressed in momentum. Remember, this is a small quantity, right? So this is that's why I say it's even harder to see. It's the hardest class of things to see. Usual momentum. So if this is really something non-relativistic, some particle coming in with low velocity, that's a small number. So compared to the case where this was m, like I had for scalar interactions, it's suppressed just because of that. And then, right, if you're scattering on something like nuclei, then at low energies you also have coherent enhancement because you scatter on all the nucleons coherently. And here you're scattering, none of that information comes in. You're scattering on the spin of the nucleus. So you're doubly suppressed. You're suppressed by your only coupling to the spin, and then you're suppressed by the momentum. So this sort of pseudo-scalar thing is super hard to see. it turns out that this is how dark matter communicates with the rest of the world. That would be very unfortunate because it's a very, very hard thing to see. All right, so this basically ends our discussion of the Yukawa theory. Are there any questions about the Yukawa theory or about our Feynman rules? I think there should be questions about the Wick theorem application because it's subtle and you're not going to know how to do it unless you do it. So that's why you have that homework. So let me know if anything in the homework is unclear. It probably is. Probably you need to supplement it. And then on Wednesday we'll start with quantum electrodynamics. All right. Yeah. Question?
Or did you say we're going to do renormalization a little more?
Well, maybe at the end, at the very end.
Okay.
Yeah. Because that's loops. So yeah. Really now the main path has been trying to do tree-level diagrams and then just showing a little bit about loops.
Yeah.
And so we're going to continue just doing tree-level diagrams with quantum electrodynamics.
Okay.
And then we'll see how to make sense of the loops. But basically what it will be is a reinterpretation of what we mean by coupling constant. And that name is really bad because it turns out that they're not constants. That's sort of the upshot of renormalization.
Okay.
That there are things that look like infinities, but again, if we're only going to be worried about measuring relative differences between a coupling, say at low energy, and a coupling at high energy, the infinity doesn't matter. It's maybe upsetting that it comes out to have an infinity, but maybe also we shouldn't be so bold as to think that the theory is valid up to arbitrary momentum scales.
Right.
And forgetting about the infinity gives rise to this nice prediction that coupling constants change with the energy scale, which is a hard thing to see for quantum electrodynamics, but for the theory of quarks is the defining feature of the theory. The fact that, I mean, that's why quarks are confined into hadrons and we never see them really, because it has extreme momentum dependence. It becomes very, very strong.
Yeah.
Yeah. So we'll try to have one or two lectures about renormalization towards the end of the class. But yeah, normally the route would be that in a first semester quantum field theory classes, there's no renormalization at all, and then the second semester is almost entirely that topic. So we won't get to spend a lot of time on it, but I want to introduce it a little. Yeah.
One other brief question. The coupling constant for QED, is that actually calculable?
No.
Will we get to that? No, okay. That's
So the number at low energy is not calculable. How it varies is calculable.
Oh, okay.
But it's just a constant.
Yeah.
Unfortunately, we don't know where it came from. But thankfully, it's a small constant.
Okay.
If it wasn't, then none of the Feynman diagram stuff would work. I mean, that scenario is realized again in the theory of quarks because there the coupling constant, the equivalent thing of charge, is big.
Yeah.
So basically, Feynman diagrams don't work very well for understanding hadrons, really. Then they work well, again, because QCD is weird, they work better at higher energies.
Okay.
So it turns out that at higher energies, the coupling constant is going down